Load theory. If you find the early versus late selection debate frustrating, well, don't be. Science is hard. An easy answer is not always a good answer. Wrestling with deep issues can be fun. But fortunately, there's also a beautiful solution in this debate. Nili Lavi has put forward what is called the load theory of attention. The basic idea is simple. The brain is smart enough to switch between early and late selection. When we are under high perceptual load, meaning the perceptual system is too busy dealing with demanding tasks, we do really early selection to get rid of a lot of stuff early on. On the other hand, when we are under low perceptual load, we do late selection because there is just not that much pressure. So why not keep things processed even up to later stages? The whole idea makes sense and has plenty of empirical support. A lot of it comes from behavioral studies. They're often very important. Don't overlook them just because they don't involve pretty pictures of brains. But in one study, they use fMRI too, which also tells us something very interesting. The experiment went like this. They required subjects to look at a screen to focus on the center, where there were a series of color crosses appearing quite fast at 750 milliseconds per item. The upright crosses were called a T, and the inverted ones an inverted T. There were two task conditions. In the low load condition, subjects had to do something relatively easy, which was just pressing a button whenever they saw something red. That meant they could ignore whether it was an upright T or an inverted T. In the high load condition, subjects had to do something a bit more demanding. They had to press a button whenever it was a yellow upright T or a green inverted T. This kind of task is sometimes called a conjunction search, which is known to be attentionally demanding because we have to look for specific combinations of features, color and upright versus inverted. Here, they had to look for not just one conjunctive-defined target, but two, so it was fairly hard. These kinds of tasks, regardless of a high load or low load, are sometimes called RSVP tasks, which stands for Rapid Serial Visual Presentation. That is, seeing a bunch of stuff happening quickly in a time in a series. Usually it involves detecting some target in the middle of the series. Importantly, while people were doing these tasks, there were flickering checkerboards in the periphery, like what is shown here in the figure. In the experiment, they were not just static, but also flickering to trigger more activity in the brain. Brain activity tends to react the most to changes with a sharp onsets and offsets. If we just present a stimulus and keep it there static, the activity saturates after a while. So, why do we need to trigger such activity with the peripheral checkerboard flicker? The rationale here is interesting. In a sense, we can consider the peripheral flicker to be a distractor, a bit like the person you're trying to ignore while you're listening to another person. So the idea is, people were meant to be attending to the center, either doing a low load or high load task. Then what happens to the distractors? Are there irrelevant peripheral flickering patterns processed? The answer is yes. But the really critical prediction of load theory concerns the difference between the low load and high load conditions. If the theory is right, under low load we should be favoring late selection, meaning we may process in the distractors more in depth, because under low load we are under a lot of pressure to filter them out early. This is what the results look like. Here, each bar concerns the activity in a region that was retinotopically specific to the peripheral distractors, not to the center letters. And on the vertical scale is the difference in bold for the low load minus the high load condition. That is how much more the brain region was reacting to the peripheral flickering distractors under low load. You see that overall these bars are positive, meaning that the brain does show more activity for the peripheral flickering distractors under low load. That's a win for load theory. But more importantly, this effect was shown in all four visual areas. Effect was bigger in later areas, but even in V1, there is clearly an effect. This is interesting because early selectionists used to claim that attentional filtering happens at a specific stage. In particular, they said even when you don't pay attention, simple physical properties like loudness, brightness are all processed the same. Attentional selection happens right before the meaning of the stimuli are processed, which is why when you attentively listen to someone else, you can still hear that person's voice. You can't
figure out the meaning of what the person is saying.
Load theory already says early selection only happens some of the time, when we are faced with very challenging perceptual tasks. But here, the results suggest something more. There's no special filter right before a specific stage of processing. It seems to be a general phenomenon applied to the processes as early as those in V1, where very simple physical features of visual stimuli are detected. So it looks like we need to understand attentional selection at a more general, on a circuit level.